Auzubillahiminash-shaytanir-rajeem. Bismillahir-Rahmanir-Rahim. Assalamu alaikum class. This is your teacher Umar Tabriz Shami for the MSc course of Advanced Power Electronics Spring 2020. Welcome to this online video lecture. I pray to Allah for the well-being of all of my students and their families. In today's online video lecture, we will start with chapter number 7. The title of this online video lecture, chapter number 7, is DC to AC converters. I have divided this chapter into 3 parts, and inshallah we will study each part in different online video lectures. Okay. So the course contents of chapter number 7 are as follows. First of all, the title is DC to AC converters, and the contents of the chapter include article 7.1 voltage source inverters. In this article we will discuss general discussion on voltage source inverters. Then article 7.1.1 is the single phase VSI standing for voltage source inverters. After single phase we will do three phase voltage source inverters, and article 7.1.3 is voltage control techniques for PWM inverters, and article 7.1.4 is current control techniques for VSI. Then is article 7.2 current source inverters. Current source inverters, we will discuss what are current source inverters, and the subsections include three phase square wave CSI standing for current source inverters, and the second article is article 7.2.2 three phase PWM CSI. So hopefully article 7.1 and 7.2 will hopefully article 7.1 and 7.2 we will cover in part number 1. Then in part number 2 I want to teach article 7.3 multi-level inverters. I only want to cover multiple I only want to cover article 7.3 in part number 2, and then in part number 3 we will cover inshallah the remaining parts of the chapter. So this is the breakup of chapter number 7. Okay. So let us now come to the first article. Okay, so the first article is 7.1 voltage source inverters. The figure 7.1 shows the VSI supplied from a diode rectifier. So let us first discuss this diagram, and then we will come to the internal structure. So in this diagram, first of all we have AC input. This AC input can be considered like our utility supplies or AC generator. Since the input is AC, therefore we convert the AC to DC using a rectifier unit. This rectifier will have pulsating DC. The ripple current will be reduced using an inductor, which is also called the DC link inductor. Here is the location of the inductor, and the pulsating voltage will be smoothened or the ripple voltages will be reduced using the DC capacitor over here. So the DC link, inductor and the capacitor are used to reduce ripple current and ripple voltage. After this comes the inverter itself. Here is the inverter. The input of the inverter is DC. We have positive voltage at the top and we have the negative voltage at the bottom. And normally we can ground over here. The inverter can be of many types. The inverter can be of many types. The inverter will always convert DC voltage to AC voltage. We can have many types of inverter. So the author has just represented one MOSFET or one IGBT. This MOSFET or IGBT represents the many types of or many configurations of inverters available. However, input of the inverter will always be DC and the output of the inverter will always be AC. Hence, the load is AC load. In this diagram specifically, the author has shown a single phase output inverter. However, we can get many phase output inverters. But the most common inverters are single phase inverter and three phase inverters as required by the load. If the load is single phase, then we need a single phase inverter. If the load is three phase, then we need a three phase inverter. Right. Now, according to the book, and I'm going to read from the book, inverters can be built with many numbers of output phases. In practice, single phase and three phase inverters are most common. However, construction of AC motors with more than three phases has recently been proposed to increase their reliability in certain critical applications. So, the most common inverter are the single phase inverter and three phase inverter. However, in recent times, AC motors with more than three phases have been proposed. They give better performance, and due to this, multi-phase inverter to drive multi-phase motor have also been proposed, and they are also gaining wide popularity. And the last sentence is that such motors have to be supplied from appropriate multi-phase inverter. So, right, next we will come to article number 7.1.3. Title is Voltage Control Techniques for PWM Inverters. So in this article we will discuss various control techniques for PWM inverters. We will discuss techniques that PWM inverters use to create variable voltage. Now there are a variety of techniques available. However, the author of our textbook has described the following four techniques. First is the carrier comparison PWM technique. Second is the space vector PWM technique, and then third is the program PWM technique, and fourth is the random PWM technique. For our course, I will focus on carrier comparison PWM technique and programmed PWM technique. Yeah. So those of my students who are interested in space vector and random, they are advised to read our textbook. Right, so now let us come to the next slide. Now in this slide, we want to discuss that out of the control techniques available, what are our desired characteristics? What do we want to achieve? So in this slide, we will discuss the desired control characteristics from voltage control techniques to drive the PWM inverter. So the first characteristic that we want is good utilization of DC supply voltage. That is, we want to use that is, the DC supply should be used, and possibly a high value of the maximum voltage gain as defined as equation number 7.12. So we want that the utilization of DC supply must be sufficient and must be good. Right, so we will now come to carrier comparison PWM technique. In this technique, first of all, this is one of the oldest techniques available for DC to AC conversion, and it's a very simple technique. Most of the technique is hardware based. So in this technique, then we use a comparator. The comparator will compare two waveforms, and an output will be produced, and this output will be a PWM output. The output, PWM output. The output will then be fed to the single phase or even three phase DC to AC converter. And this is the inverter, and we are controlling these four switches. So in the next slide, and yes, here is the truth table, and we will discuss this truth table in the next slide. So we will now discuss the detailed working of carrier comparison PWM technique. In this technique, we use, first of all, we use a comparator. The comparator is an operational amplifier with two inputs and one output. The output is digital. Okay. The comparator has two inputs. First, one input is called the inverting input, that is V minus, and the second input is called the non-inverting input, that is V positive. These are just simple names given to the terminals. Using tradition, the comparator has two inputs, the inverting input and the non-inverting input, V minus, V positive. This V minus and V positive are just simple labels. There is no restriction of voltage polarity. We can supply positive or negative to either inputs. So if we are dealing with V positive, it doesn't matter if we give a negative input or the positive input. Likewise, for the inverting input, it doesn't matter if we give positive input or negative input, positive polarity or negative polarity, provided the biasing is positive or negative. That is natural. However, in this case, we will supply, it is very important to note that in this case, since the comparator is biased with some plus VCC and ground, therefore both input voltages will be positive. This is important to know, right? So coming back to the carrier comparison, V minus, V negative represents the inverting input and V positive represents the non-inverting input. We will provide a carrier wave
which is normally a triangular waveform of much higher frequency. We will connect the carrier wave, the triangular wave, to the inverting input, that is V minus, and we will connect the modulating signal, or the signal that we want to compare the triangle wave with, that is the modulating signal, to the V positive input or the non-inverting input. Now comes the output. Output will be digital, that is, output will be either 0 or 1. Output will be digital, it will be 0 or 1. When will it be 0 and when will it be 1? Output V out over here, V out will be 1 only if V positive is larger than V negative. This is the only condition this is the only condition when V out will be logic 1, when V positive or the non-inverting input voltage is larger than the inverting input, and output voltage will be logic 0 only when V positive is smaller than V negative. Output voltage will be 0 when V positive is smaller than V negative, or when the voltage at non-inverting input is smaller than the voltage at inverting input. Now there is another third case is also, the third case is also, the third case can also be positive, can also be possible when V positive is equal to V negative. So when we compare two items, or when we compare two signals, there are three possibilities. First possibility is that one signal is larger than the other. Second possibility is that the first signal is smaller than the other. And the third possibility is that both of signals are the same. If the V positive is larger than V negative, output is logic 1. If V positive is smaller than V negative, output is logic 0. But what will happen when both of them are equal? Then please note that V out will be equal to 0, logic 0. So when both signals are equal, at that time output V out will be logic 0. Right. Now, what we have done is that we have connected a carrier wave to the we have connected a carrier wave to the inverting signal, a modulating signal to the non-inverting input. The comparator compares the two signals and produces an output. The output is digital. So since we are driving a single phase inverter where the power switches are Q1, Q2, Q3 and Q4. Q1, let us look at Q1 and Q4. Q1 and Q4 Q1 and Q4 cannot be turned on at the same time. They will work as a complementary pair. When one is on, the other is off. Likewise, let us look at Q3 and Q2. They are also working, since they are working in the same phase, then they cannot be turned on at the same time. So Q3 and Q2 are also working as a complementary. That is, when one is on, the other is off. Therefore, let us look at the output of the comparator. We take two outputs. First output is directly given to Q1 and Q2. This is Q1 and this is Q2. So Q1 and Q2. That looks very logical. Yes. And now comes the second part. That output of the comparator is also provided to an inverter, that is a NOT gate. This is the NOT gate. So when we have logic 1 at the input of the NOT gate, we produce logic 0. When we have logic 0 at the input of the NOT gate, we have logic mode. Output of the NOT gate is given to Q3 and Q4. This is Q3 and this is Q4. Q4 is over here. Therefore, Q1 and Q4 are working as a complementary, and Q3 and Q2 are also working as a complementary. Q1 and Q4, they are working as a complementary, and Q2 and Q3, they are also working as a complement. So this is a very simple arrangement through which we can drive a single phase inverter. Right, in the next diagram, in this diagram, what we have is the red colored signal represents the carrier signal. The triangular waveform represents the carrier signal. Whereas we must also note that the carrier signal has much large frequency, and then the blue colored signal represents the modulating signal. We can note there are a few things that we should note over here. First thing is that the carrier signal, the triangular waveform, has much large frequency as compared to the modulating signal, the blue colored, as compared to the blue colored signal, our modulating signal. The modulating signal has a lower frequency, whereas the carrier signal has a much larger frequency. There is another important thing that all of my students should know, and that is the biasing. The biasing of carrier signal and modulating signal. All my students should look very carefully that both of the signals, either modulating signal or the carrier signals, both are DC voltage in nature. They might look AC, but they are not AC. Both are DC. And we must, this is a very important note this is a very important point to note, that both voltages being provided to the comparator must be positive signals, must be, if the biasing is positive, which I have shown over here, biasing is positive. Therefore, the modulating signal and the carrier signals must both be positive. So in this graph, the signals, they appear to be AC, but they are not AC, they are DC. However, the DC, let us look at the y-axis. On the y-axis is the minimum voltage is 0 and the maximum voltage is 7500 millivolts. Both signals do not have any negative voltage. Both are DC. So, and after this we do the comparison. We make both signals DC and then we do the comparison. So how is it possible to convert an AC signal into a DC signal? Let us look at the modulating signal. It looks like a sine wave, but it is a sine wave with some DC voltage. So this is this dash line represents the DC voltage on which we add the sine wave, so that the positive half, so that the sine wave from 0 to pi is positive, and also the voltage from pi to 2 pi, which used to be negative, is now also positive. After then we do the comparison. So the modulating signal, the sine wave has been superimposed by a DC voltage. After this we get a modulating signal that is always positive from 0 to 2 pi. Same is the case with carrier signal. We have superimposed a triangular waveform with a DC voltage so that we shift the triangular waveform to entirely into the first quadrant, and we make carrier signal and modulating signal both positive. After then, the comparison is done, and the comparison is the PWM. Here is the PWM over here, the PWM, and on the waveform this is the PWM, and here is the PWM signal. Since it is digital, it will only have two states: logic 0, low, or logic 1, that is high. And this is the carrier, and this is the PWM output. This will be the PWM output for Q1 and Q2. This will be the carrier, this will be the PWM output for Q1 and Q2. And the complementary of this signal, that is the not function of this signal, will be the control signal for Q3 and Q4 as shown in the circuit diagram. Okay. So, however, this circuit only demonstrated single phase. How do we obtain a three-phase inverter with carrier comparison technique? This will be shown in the next slide. So in the next slide, a little bit complex, but it's quite easy to understand. The concept is the same. In this slide, we will discuss the comparison technique for PWM, the carrier comparison technique for PWM for three-phase inverter. So let us look at the circuit one by one. First of all, we have S1, S3, S5, S4, S6 and S2. They make up our DC to AC three-phase inverter. First, let us recognize that this is our inverter. Here is the input DC voltage, positive terminal, negative terminal, and then comes the 6 power electronic switches from S1 to S6, and they make up the three-phase inverter. Then we have phase A, phase B and phase C as our outputs. Three outputs: phase A, phase B and phase C. After this, there is the three-phase induction motor, which we are assuming as our load. Okay. So of course this circuit is the simulation circuit which my students they can find in MATLAB. Okay, but the actual circuit will also look very similar to this one. Now, what is being done? This is an optional circuit. This is an optional configuration. It's not a part of our main circuit. This is a part of MATLAB simulation where voltages, the line-to-line voltages can be measured. Likewise, the current in each phase can also be measured. However, this is not a part of our main circuit. This is just explanation of the diagram. Now comes the control unit. The control unit is over here. This is the control unit. Here is a control unit. The technique, as I mentioned earlier, the technique or the concept will remain the same, that we will have a carrier signal and we will have a modulating signal. And yes, the modulating signal is also called the reference signal. In three-phase case, we will use three sine waves: sine wave A, sine wave B and sine wave C as the modulating signals or the reference signals. Now, since this is a three-phase inverter where output voltages VA, VB and VC, they must have a phase difference of 120 degrees. So we have to be very careful that the modulating signals sine A, sine B and sine C are also experiencing, or they have also a phase difference of 120 degree. Otherwise our inverter will not work correct. So sine A, sine B and sine C, sine wave A, sine wave B, sine wave C are the modulating signal. They are the reference signal. They will have equal peak to peak voltages and they will have phase difference of 120 degree from each other. Then, then we are using three comparators. One, two, three. Three comparators. Each comparator has two inputs. One input comes from the modulating signal and the second input comes from a common triangular waveform. This is the same triangular waveform which we call the carrier signal. So let us look at the first comparator. The first comparator has two inputs. First input from sine wave A and second input from the triangular waveform. And then the comparator will compare, it will produce a digital or logical output. Then the S1 will be directly fed from the comparator, whereas S4, this is S4 over here, S4 will be given a signal after the inversion or after performing NOT function of first comparator. This is exactly the same concept as we did in the previous slide, right? So sine A and the carrier signal, after being compared, they are given to the phase A of the inverter. Then let us look at the second phase B. Phase B has S3 and S6. They are being controlled from sine B. The second comparator has again two inputs. One input is sine B and the second input same coming from the same triangular waveform into the second comparator. And the second comparator produces an output which goes straight to S3, whereas S6 is being controlled after the comparator signal is fed to NOT gate or to the inverter and then given to S6. So this was the control circuit for phase B. Now let us look at phase C. Phase C has again two power switches, S5 and S2. They are being controlled from the third comparator. The third comparator again has two inputs. One is sine wave C and the second input is coming from the same carrier waveform, triangular waveform. And when the comparator produces an output, first output is given straight to the gate of switch S5, whereas when the comparator output is given to the NOT gate, and after the NOT gate we can control switch S2. So in this sequence we are controlling a three-phase inverter. Concept is the same, however we have slightly modified using three sine wave with 120 degree phase difference. We have slightly modified the control sequence. Okay. The output is then given to the three-phase load, which in our case is a three-phase induction motor, and the voltages can be measured, the current can be measured. Now, before we come to the next slide, let us just now, before we come to the next article, a few words, few closing words about carrier comparison, PWM technique. That if we look back to the slides that we covered earlier, that in PWM case, yes, over here, in PWM case,
in PWM case, we always have a certain number of harmonics, low order harmonics, and we can reduce them by controlling the pulses. Now there is another technique to especially use to eliminate the third harmonic, because the third harmonic will have the largest strength after the first harmonic, and we can reduce this by using a special modulating signal called the third harmonic modulating function. That is, instead of using a regular sine wave, we use a third harmonic injected modulating function, and this is the waveform of the third harmonic injected modulating signal, and it is obtained by adding the first harmonic with the third harmonic. We get the third harmonic injected carrier, we get the third harmonic modulating signal. If we use this special function as our modulating function, as and we compare it with the carrier signal, then the resulting PWM will be free from third harmonics. So this was just the closing remarks for the carrier comparison. So this brings us to the end of uh, carrier comparison PWM technique. And after this, we will come to our uh, program technique. After this, we will come to the program PWM technique. Right. So now we will come to the programmed PWM techniques for DC to AC inverters. This technique is very interesting, and it is employed using microprocessors, including computers or microcontrollers. The scheme is very simple. The scheme is that we have a normal three-phase inverter, and the three-phase inverter output is connected to a three-phase load. Then, to control the switching of the 6 power switches, we will use a microcontroller. In this case, we are using a microcontroller, but we can use DSP cards, microcomputer, or even uh, or even some FPGA. Now, the meaning of program PWM is that inside the microcontroller, we will write a code. We will write a computer code which will turn on or off all of the 6 power electronic switches. So the flow of control will be that the microcontroller will execute a program. This program will be written by a programmer, normally the engineer. This program will produce 6 control signals. In our case, it is PWM0, PWM1, PWM2, 3, 4, and 5. These 6 control signals will then be given to the driver. This driver will produce enough strength in the signal and sufficient voltage level to turn on or off our 6 power electronic switches. And the result will be that the output will be a PWM. So we don't need any comparator, we don't need any analog circuit to turn on or off the 6 power electronic switches. Okay. So, for example, in this diagram, this is the output of one phase. What we will do is that we observe that from 0 to alpha 1, the output is 0. Then from alpha 1 to alpha 2, the output is VTC. Then from alpha 2 to alpha 3, the output is 0 again. And then from alpha 3 to alpha 4, the output is plus VTC. And then from alpha 4 to alpha 5, output is 0. Then from alpha 5 to pi by 2, the output is 1, and the rest is um, the symmetry. The rest of the waveform is completed by the quarter wave symmetry. Now, if we feed the values of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, or even more angles, if we feed the values of firing angle alpha 1, 2, 3, and 4 inside into the microcontroller, then this becomes a programmed PWM. So this means that we are training the microcontroller, or we have written a code to the microcontroller, and the microcontroller will execute the switching. So we will feed the values of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 inside the microcontroller, and we will allow the microcontroller to run in a forever loop. So by this way, the program so the so by this way the microcontroller will continue operating the 6 control signals, and the driver will continue to turn on or off our 6 power electronics devices, and as a result we will have 3-phase output to the load. My students, they can also relate that this technique can also be applied to single phase inverters also. However, there is a condition that for maintaining the quarter wave symmetry, the angles of alpha 1, alpha 2, alpha 3 have a limit from 0 degree to pi by 2. That is, alpha 1, alpha 2, alpha 3 should all be within 0 degree to 90 degree, such that alpha 1 is larger is larger than 0 degrees, alpha 2 is larger than alpha 1 or equal to alpha 1, and alpha 3 is larger than alpha 2, and so on. So this is a constraint that we have to maintain. Now we can feed the angles from alpha 1 to alpha 2, alpha 3, and so on in the microcontroller, and we will get a program PWM. So in the in a easy case, if we want to establish, if we want to get square wave, then we can program PWM 0 to PWM 5 to be on from 0 to pi, and then to be off from pi to 2 pi, and then we can so so this means that to get program PWM, we need the angles alpha 1, alpha 2, alpha 3. Now alpha 1, alpha 2, alpha 3 and onwards, they can be obtained in a number of ways. First, we can program them graphically. We can make up of a program graphically and feed the angles into the microcontroller. However, such technique will have a lot of harmonics. So the alternate technique that we will use for program PWM technique to find alpha 1, alpha 2, alpha 3 is called selective harmonic elimination. And this is what we'll do in the next slide. So in the next slide, we will develop a PWM signal. From this, we will develop a graphical PWM signal. From this graphical PWM, we will develop a Fourier series. From the Fourier series, we will find the angles alpha 1, alpha 2, alpha 3, and so on. So in this slide, let us consider a PWM waveform. This is a PWM waveform from 0 to 2 pi, and alpha naught, alpha 1, alpha 2, alpha 3 are our switching angles. They are called switching angles. This is the graphical representation of our PWM wave, and from this graphical representation we will derive a mathematical function of the PWM waveform, and we will use Fourier series to represent our waveform. So a Fourier series can represent the waveform as follows. This is the general equation for a Fourier series. That is, function f of x is equal to a naught plus summation bracket a n cos n x plus b n sin n x, where alpha naught, a naught, a n, and b n are coefficient constants, are coefficients, such that a naught is equal to 1 over 2 pi integral 0 to 2 pi vdc d omega t. A n is 1 over pi integral 0 to 2 pi vdc cos n omega t d omega t, and bn is equal to 1 over pi integral 0 to 2 pi vdc sin n omega t d omega t. So our general procedure to develop a mathematical function of a given graphical waveform is to find the coefficients a naught, a n, and b n, and then place them back into the general equation, and hence we get the mathematical function of a given graphical wave. And this is what we will do. Right, in the next slide we will develop a mathematical waveform of our PWM. So let us look at the waveform. This is our waveform whose mathematical function we want to derive. It has quarter symmetry. That means that the waveform is symmetrical quarterly. That is, from 0 to 90 degree, whatever is a function of the wave, the remaining quarters have the similar functions. That is, whatever is the angle a naught, alpha naught, alpha 1, alpha 2, alpha 3 are the same for the remaining 3 quarters of the waveform. And this fact will help us to develop the mathematical expression. So due to the quarter wave symmetry of output voltage, even harmonics are absent. Therefore, the coefficient an and a naught are 0. Therefore, the coefficients a naught is 0 and an is 0. A naught is also, we can also see that why a naught is 0, because there is no DC component in our AC signal. That is another reason why a naught is 0. Then due to the absence of even harmonics, because it is symmetrical waveform, therefore the coefficient an is also equal to 0. So we are only left to solve bn, and bn is given by 1 over integral 0 integral 1 over pi integral 0 to 2 pi vdc sin n omega t d omega t. Hence our function, our Fourier series is equal to, I am replacing x by omega t. I'm replacing this x. I'm replacing this x by omega t. Now a naught is 0, an is 0. So all of these two terms become 0, and I am replacing f by the voltage. So v omega t is equal to bn sin n x, sin n omega t. So we are left with voltage v omega t is equal to summation n 1 to infinity bn sine n omega t. Now what we have to do is that we have to find bn. We have to find bn for for bipolar waveform. This is your normal bipolar PWM. The definition of bipolar PWM is that it's a PWM signal which has two states, either positive voltage or negative voltage from 0 to pi. This is a bipolar waveform. And to solve for bipolar waveform, the expression Bn is expanded with regard to number of switching angles and fundamental output for bipolar PWM. That is, Bn now becomes or is expressed as Bn is equal to 1 over n pi. Bn is equal to 4 over n pi bracket minus 1 minus 2 summation I is equal to 1 to n bracket 1 minus n to the power I cos n alpha I, where alpha I is the switching angles. So this is the equation for Bn. We return this function, we place this function into Bn, and we get the mathematical expression of our graphical waveform with the switching angle still unknown, right? So in the next slide I will expand Bn. So here I have expanded Bn. Bn takes this form. Now in this equation we have to find, it should be alpha I. Anyways, it's changed to K2. Please note this changes that in this equation I has been replaced by K. So we have to find alpha I or alpha K. The alpha I or alpha K are our switching angles. Where are the switching angles? Here is the switching angle. These are the switching angles. Alpha naught, alpha 1, alpha 2, alpha 3. So I'm sorry for this changing in alpha I is written over here, but here it is written alpha K, but it is the same thing. Alpha I and alpha K represent the same thing. So we have to find alpha I or alpha K. We can do this by expanding or by inserting the value of alpha I, and this will be done by expanding or placing alpha K as separate variables, and we get this matrix. Now what is this matrix? This matrix represent the harmonics in our mathematical function of the waveform, where the first equation is when this n is kept to 1, that is the fundamental component, and then the third n is 3 over here. This means that it is the third component, and then the fifth, and then the seventh. So remember that in this wave symmetry, the odd number of harmonics are present, but the even number of harmonics are absent. Therefore, we are taking only n is equal to 1, 3, 5, and 7. This is the matrix, and we will solve the above matrix for alpha 1, alpha 2, alpha 3, and alpha 4. And when we solve for this, what do we get? We get our switching angles 1, 2, 3, 4. And these switching angles will now be programmed into the microcontroller, and the microcontroller will be allowed to run in a forever loop. And by doing so, our switches, they will operate producing such waveform. So let us talk about this matrix. What we have done is we have allowed the first harmonic to be equal to this amount, and then we have allowed the third harmonic, the fifth harmonic, the seventh harmonic to be equal to 0. We have purposely set the third harmonic to be equal to 0, the fifth harmonic to be equal to 0, and the seventh harmonic to be equal to 0. And here this procedure where we are specifically or purposely stating that the third, the fifth, and the seventh harmonic should be 0. We want angles alpha 1, alpha 2, alpha 3 such that we have this as our first harmonic, and our first harmonic to be equal to this amount, and the third, the fifth, and the seventh harmonic to be set to 0. Hence, we are eliminating third, fifth, and seventh harmonic purposely. So we will solve this matrix. We will solve for alpha 1, alpha 2, alpha 3, alpha 4, and alpha 4 so that we have first harmonic, but the third, the fifth, the seventh harmonic are set to 0. And this is called selective harmonic elimination. Now, how do we solve this? We can solve this by iteration methods. We will solve this. We can solve this by Newton-Raphson or iteration method, and this will be solved using MATLAB or Mathematica simulation software. And when we run this, we can solve. When we run this, and we can solve for values of alpha 1 to alpha 4. Now, and this is what our output result will look like. We will get a waveform like this. We will get a waveform like this. We will get a waveform like this. And when we perform the harmonic analysis will look like this. The harmonic analysis will look like this, where the third, the fifth, and the seventh harmonics have been eliminated. Why have been eliminated? Because we purposely set the third, the fifth, the seventh to equal to 0. We wanted angles alpha 1, alpha 2, alpha 3, and alpha 4 such that these four equations are true, such that alpha 1, we want alpha 1, alpha 2, alpha 3, alpha 4 such that the third, the fifth, and the seventh harmonics are 0. And the result is that we get values of alpha 1, alpha 2, alpha 3, alpha 4. We get those values within the range from 0 to 90 so that the harmonics are eliminated. So we have the first component almost equal to 1, and the third, the fifth, the seventh are eliminated. Now, why the ninth and the 11th are not eliminated? Because we are using a, if I can go back, a 4 by 4 matrix. If we want to eliminate the ninth and 11th, then we will expand this equation up to alpha 5 and alpha 6 also. So, but this will increase the computation time, and I'm showing just for an example, but we can do this. So this is the result, that harmonics have been eliminated, and the higher order harmonics, the 9th, 11th, 13th, either they can be run like this or they can be eliminated or attenuated using filters. So after the okay. So this I would like to show some calculations that I did earlier. I calculated the values. I calculated the values of alpha 1, alpha 2, alpha 3, and this is the waveform that I got. And here is the frequency analysis. Then we can see that they here the third, the fifth, and the seventh frequencies have been eliminated. So this is a very useful technique where after solving the equation we get the values of alpha of all the alphas, and then we program and then we place the value of alpha back into the microcontroller, and we allow the microcontroller to execute in a forever loop, and we get a waveform like the one shown. And when the frequency spectrum, the same waveform is shown over here. Harmonics have been eliminated. Harmonics have been eliminated. Okay. So now, as we can see that in this diagram, we can eliminate more harmonics. As we go on expanding our matrix, we can eliminate more harmonics. So in this diagram, the first is present, but the fifth, the seventh, the 11th, 13th, 17th, 19th, 23rd, 29th, the 31st harmonics have been eliminated. And this is the wave shape, and here is the frequency spectrum. And finally, these are the optimal primary switching angles from alpha 1 to alpha 5, and these are the angles for output voltage versus the value of the angles. So this graph shows on the x-axis the output voltage. Output voltage. How do we get the output voltage? We will get output voltage by changing the value of voltage of the first component over here, and then we can, if we want to change the output voltage, we can reprogram, or we can find the values of alpha 1 to alpha 4 for various voltages from 0 to 1. And as a result, what will happen is that we get a waveform of alpha 1 to alpha 2, alpha 3, alpha 4, alpha 5 for changing the voltage level from 0 to 1, and on the y-axis is the angle values itself. So this is a very useful technique to be programmed into the microcontroller, and though no analog hardware is required, we can figure out the angles alpha 1 to alpha 5 or as much as we like by performing simulations, and then from the simulation the angles can be transferred into controller, and the controller can execute the switching. Right. One more thing, one important thing to note is that when we solve this matrix for alpha 1, alpha 2, alpha 3, alpha 4, this we use iterative methods, and here it is written that the above matrix can be solved by iteration method, for example Newton-Raphson method. Now please remember that Newton-Raphson method is only one technique. We can employ many optimization algorithms to solve for the switching angles. For example, we can apply genetic code optimization, or the PSO method, or for solving to finding the best solutions for alpha 1, alpha 2, alpha 3, alpha 4. Because these are non-linear equations, and we will solve for best answers, and there are a number of optimization algorithms which we can employ. So PSO or genetic algorithm are two examples. So, and this becomes a good area for research also, where the students can investigate number of algorithms, optimization algorithms for specifically calculating the switching angles for selective harmonic eliminations. Okay, so do keep this in mind. So this brings us to the end of our first part. Thank you very much for your time. Thank you very much for listening to me. Please note that I would urge all of my students to do the book reading also. So thank you very much. अल्लाह ताला आप सबको अपनी खास हिफ्ज़-ओ-मान में रखे. इंशाल्लाह ताला नेक्स्ट ऑनलाइन लेक्चर में मुलाकात होगी. अस्सलाम वालेकुम.